about some ongoing work which has the aim of understanding the combinatorics of higher degree polynomials, complex polynomials in one variable when one regards them as dynamical systems. So let me first introduce the basic objects that we're going to be dealing with. Those are polynomials from the complex plane to the complex plane, and up to affine conjugacy, one can always consider them monic and without the term d minus 1. And one is interested in seeing what happens to the points as one iterates the function. This means f composed with itself n times. And the first thing that one observes is that there are always points that under iterations of f escape to infinity. That is what we call the basin of infinity, which we'll denote by omega of f. And then there are the points that don't escape to infinity, which is called the field-Julia set. And the common boundary of these two sets is the set where the exciting things happen and concentrates the chaotic dynamic of the polynomial. So mainly understanding the dynamic of the polynomial is closely related to understanding what goes on over the Julia set. So these are the basic objects, and then since one can go to a computer and draw a few pictures and see what happens. And those are pictures of some random polynomials, well, not so random, but what one first observes is that these sets come in different flavors. Some of them separate the plane and some do not, and some are disconnected and some are not. So we're going mainly to talk about today is about Julia sets which are connected, or polynomials which have connected Julia set. So our standing assumption is going to be that the Julia set is connected. And under that assumption, the basin of infinity when one adjoins to the basin of infinity the point in infinity that is conformally isomorphic to the unit disk, and it's better to write the conformal isomorphism with the complement of the unit disk. Let's call this map phi, which is the Bether coordinate. Well, not yet. And it turns out that there's a unique such map which is asymptotic to the identity at infinity and has the property that conjugates the dynamics of C goes to C to the D to the dynamics of the polynomial. So that means, well, whatever the functional relation is, if one goes here first and then here, is the same as going here and then here. So that means that we have a pretty good description of what happens in the basin of infinity when the Julia set is connected. And the temptation is to then go towards the Julia set, go towards the boundary of the basin of infinity and try to extend our understanding of the dynamics in the basin of infinity to an understanding of the dynamics over the Julia set. And of course, if the best situation possible is the one in which this map extends continuously to the boundary of the unit disk. So that is the case when the Julia set is locally connected. We have an extension phi bar of phi from the complement of the open disk to the basin of infinity together with the Julia set. And the dynamics of the disk power over the boundary of the unit disk is just like multiplication by d of the angles in the boundary of the unit disk goes to the dynamics of applying the function f in the Julia set. So in that case, one can reconstruct easily the Julia set. So by introducing an equivalence relation which identifies T with T prime if the of the unit disk map to the same point. So whenever we have a continuous extension, we have this equivalence relation. So let me, and this is of course, so one can try to draw this equivalence relation in some way, and it turns out that a very practical way to do it is to take the convex hull of equivalence classes in the closed unit disk with respect to the hyperbolic metric. By that I mean that if one has 2 points which are equivalent, then one can draw the geodesic chord that joins them in the unit disk. If one has 3 points, just draw the triangle. If one has 1 point, in if an equivalence class of lambda r is just 1 point, just draw 1 point. So let me give an example here. That is a cubic polynomial, and which has Julia set, which is locally connected. And if one analyzes the continuous extension of that map phi, which is the Bether map, one can show that these 6 angles go to that. This one here comes here, this one here comes here, and these 2 come over here. And one can represent those equivalence classes by taking just the convex hull of the corresponding elements in the boundary of the unit disk. And it turns out that these convex hulls are disjoint, and that the union of the leaves in the boundary of these convex hulls form a geodesic lamination. And this is sort of a a very simple example of geodesic lamination, but it is very graphic to represent the topology of certain Julia sets. And how can one recover the topology of the Julia set from this way of representing the equivalence relation lambda r is just by collapsing these convex holes, one obtains again certain subset of the plane. More precisely, one can think of the pair, the complex plane, and collapse the convex holes of the equivalence relations of lambda r. The unit S collapse the equivalence relations. And in the case that the Julia set is locally connected, this turns out to be homeomorphic to the pair, the Julia set, the complex plane, and the field Julia set. That is in the case that things are locally connected. But this is too good to be true. The Julia set is not always locally connected, and one has to get a hold of the topology of the Julia set, but by analyzing more in detail the boundary behavior of this map. So that is done following Dodi and Hubbard through external rays. So an external ray is the image of a radial line coming out with angle T under this map, well, different phi, under the map P. So an external ray in the dynamical plane is just the image of this line here. And one analyzes what happens as one approaches the Julia set along an external ray. And one says that that external ray lands at a point if it has a well-defined limit. And the basic things to observe here is that external rays map onto external rays by the map F, is here. So this is the external ray, for example, with angle 1,7, and that maps by F onto the external ray. This is a quadratic polynomial onto external ray with angle 2/7. And the landing points map under F to the landing point of the corresponding image ray. So one would like to know when there is which external rays have a well-defined limit, or when external rays do land. It turns out that Dodi and Hubbard proved that if T belongs to Q mod C, then the external ray lands, has a well-defined limit. Oh, I dropped the assumption locally connected. Forget about this. So now what we're doing is sort of the ideal case was when it was locally connected, but that is too much to ask. So one starts studying what is true in general. And it's still connected. Still connected. That is an assumption. This is an assumption now, and this is not. Okay? So it lands, and moreover it lands at periodic or pre-periodic points. And these periodic points, the periodic points are which are the landing point of rational rays are either repelling or parabolic. And it turns out that the converse is also true. Dodi, Hubbard, Sullivan, Jocose. If one has a repelling or parabolic periodic point, then C is the landing point. Of a rational ray. Of at least one, and really at most finitely many. So in some sense we have something to get a hold on to study the topology of the Julia set. And what I will understand as the combinatorics associated to a polynomial is to study the landing pattern of the rational rays. The landing points are dense in the Julia set, yeah. So what is the rational lamination? Is the equivalence relation in Q mod C, which identifies two elements of Q mod C, two rational elements of the circle, if the rays land at a common point. Okay? So, what the question is, well, why to study such objects? Why one should think that this captures a lot of information about the Julia set? I will try to convince you that that is so, but there are also some sort of evidence that first, clearly this object is connected with the topology of the Julia set. So by studying this object, one can sort of get an understanding of the topological dynamics over the Julia set. Second, it sort of is a simple object which will allow us to compare different dynamical systems. If they have the same rational lamination or if they don't, I mean, it allows us to compare and hence to start giving a rough classification of different dynamical behavior. And third, turns out that when one studies the quadratic, the set of quadratic polynomials, all the Dwadi-Hubbard description of this parameter space is closely connected with the rational lamination of the polynomials. That is, one can understand a lot of how different dynamical behavior is organized in parameter space through understanding their rational lamination. So those are sort of three motivations. So to start, one would like to answer the questions of which equivalence relations appear as the rational lamination of a polynomial. What are the set of all possibilities? And hopefully one could then start understanding where in parameter space one can find polynomials with rational laminations that have certain properties. I would mainly refer to this question today to sort of try to characterize the rational lamination of complex polynomials. The first thing that one does then is to take a look to the basic properties of the rational lamination. I will explain these basic properties. The rational lamination as a subset of Q mod C cross Q mod C is a closed set. Each equivalence class is finite. That follows from these results that I put here. They're pairwise and linked. The equivalence classes means that if one takes two equivalence classes and takes the corresponding convex hull in the closed unit disk, then they're disjoint. There are certain invariants. If one has an equivalence class, then by multiplying by D, one gets again an equivalence class. And there are certain order preserving property, which comes from the fact that the polynomial is an orientation preserving map. Let me explain with a picture what I mean by that. So let me explain what means consecutive preserving by explaining here what was on. If one looks at this map, 1/7, 2/7, and 4/7 is an equivalence class. It's rational lamination. And then the landing point here happens to be a fixed point, and 1/7 maps to 2/7, maps to 4/7, and that maps back to 1/7. So the cyclic order here is preserved. When one looks at the preimage here of this point, one gets 1/14, 9/14, and 11. So then this maps over here, the one that comes next maps over here, and the one that comes next maps over here. So also the cyclic order is preserved. The consecutive preserving property essentially what captures is that. And finally, one has a polynomial which has all cycles repelling, then one can prove an extra property, that is that the rational lamination is maximal with respect to these 5 simple properties. We expect that these 5 simple properties characterize the rational lamination of a polynomial. We can prove that a corresponding statement only for polynomials with all cycles repelling. Yeah, maximal with respect, the order is inclusion. So the theorem is that is the rational lamination of a polynomial with all cycles repelling. If and only if lambda q satisfies 1 through 5 and is maximal. Of course, this is sort of the abstract part of the characterization. There's a more constructive part. So let me come back to these properties. So in these properties, there are only two which are more sort of global nature, which deal with how all the equivalence classes of these equivalence relations are organized. And those are the only maybe non-immediate properties that the rational lamination has. And let me at least comment on those properties. The closed property, a warm-up observation for the closed property is the following. Imagine that one has a Julia set. With two fixed points which are the landing of fixed rays. Fixed rays have to be of the form k over d minus 1 under multiplication by d mod 1. Those are the fixed points. Then it is easy to see that there's some preimage of this external ray which lands here in the middle. I'll put it chi. Some iterated preimage. So that is sort of the warm-up observation. Between two any fixed rays, there's some preimage of one of them that lands in the middle. This is fairly obvious. But now when one wants to prove that the rational lamination is closed, what one does is one has a series a sequence of rays Tn Sn which are converging to some ray T and S in Q mod C, and this sequence of rays are landing at the same point, and one would like to show that if these two are rational, they land at the same point. So well, and here the Julia set continues, of course. So with some work, what one does is shows that there's a smaller Julia set around here. I forgot to say something. So to show that something is closed, what one has to show is that if this converges to this and this converges to that, then the limiting, if these rays with these corresponding arguments are landing at the same point, then one wants these two landing at the same point. One can easily restrict to the case where these two arguments are fixed arguments, are arguments fixed by multiplication by d. So this ray goes to itself and this other ray goes to itself. Then one finds a smaller Julia set inside here with some standard techniques and shows that there's some preimage of this fixed ray for this small Julia set, the pink one, that is in this side. And that has to land in the pink Julia set. And that contradicts the fact that the external rays are disjoint, and that could only happen if S and T were landing at the same point. So that is more or less a very sketchy idea of how one proves the closed property of the rational lamination. For some polynomial like that one extracts, yeah. Some ad hoc polynomial. So that is the part that one has to work a little bit, is to extract the pink Julia set somehow. Okay. So, and actually, the proof of this says much more, says that the topology, when one comes from the side of the SN-TNs of the Julia set, is quite mild, that the landing points converge to the landing point. Now let me comment in the maximal, about the maximal property of the rational laminations when they have all cycles repelling, when the polynomial in question has all cycles repelling. And maximality comes from analyzing the possible pictures on equivalence classes, which are either polygons, leaves, or points. And what one shows is that there are no isolated leaves in certain sense when one represents irrational lamination as a convex hull equivalence class. That there are other elements of the rational lamination which approximate each of the leaves. And here, from both sides, the same picture. One has sequence of equivalence classes which are converging to each side of the leaves, and here like this. So it would be hard to extend a rational lamination to find a bigger one which has its picture, which has a picture around each equivalence class, like the pink one, because if one wants to add a point to the pink one would have to be able to draw this picture, but that picture intersects infinitely many other equivalence classes, and that cannot be, violates the unlinked property. And here the same, and here the same idea. One cannot, that equivalence relation for polynomials with all cycles repelling is already saturated. So let me explain where the repelling cycles come in. That is definitely not true if one drops that hypothesis. And so the repelling cycles come in when one applies this incredible inequality. So that is sort of the essential part of the argument. So what is d minus 1 here? D minus 1, if one has from R mod C to R mod C the multiplication by D map, I already said that the fixed points of this map are of the form something over D minus 1. So this has D minus 1 fixed points. And a polynomial of degree D, unless one has a multiple fixed point, one has D fixed points. So when a polynomial of degree D has all fixed points repelling, there are no multiple fixed points and there are D fixed points. D fixed points of F. And now what the Dwadi, Hubbard, Jacob, Sullivan theorems say about landing rays. Well, one has D minus 1 fixed rays, which at most can cover D minus 1 fixed points, but there is a fixed point, which is the landing point of some periodic ray, which is not covered by the fixed rays. Okay, so then one has some periodic ray has to land there of some period, say 3, and one would have a point with more than one ray landing at it. So whenever one has all the fixed point repelling, immediately that means that by this inequality one has a non-trivial rational lamination. Okay? One has at least one equivalence class which contains more than one element. And now one applies sort of the same idea that for closed, is that if this were not the picture, was not the picture, then one can extract sort of small Julia set where there is a fixed point with only fixed rays, where all the fixed points are only landing points of fixed rays, and that gets a contradiction. Okay. So that is the comment about the basic properties of the rational lamination. So this study of how the basic properties of the rational lamination, in particular the maximal property, give nice corollaries about the topology of the Julia set. It means that one controls the topology of the Julia set around periodic points, around the repelling periodic points, and one knows that then it's not difficult to conclude from this picture that the Julia set is locally connected at repelling at periodic points. So automatically when one has all cycles repelling, one has that the topology of the Julia set is sort of tame around the periodic and pre-periodic points. But what about the rest? So here we have analyzed the basic properties of rational lamination, but the rational lamination, what happens with the rest of the external rays and with the rest of arguments in the circle. And one interesting property that, again, continuing with all cycles repelling, is that one has the rational lamination again. One represents the rational lamination as the union of the convex hull of the equivalence classes. And one asks how each connected component of the complement looks like. And one proves that each connected component of, say, the disk minus the convex hull of each equivalence class of lambda q is a finite-sided polygon. It's finite-sided. That is, if one takes a look now not only at the rational points of the circle, but at the rational points of the circle, what is left in a connected component outside this convex hull with vertices in the rational is only finite-sided polygons. And this is this leads to the following. So the rational lamination is a closed set in Q mod C, but not a closed set in R mod C. So that's the main problem. And Q mod C is not a very nice set to be closed in. So since it's a finite-sided polygon, the complement, this means that we want to extend the rational lamination not only now to extend it to an equivalence relation in R mod C, one has essentially only one way to close this equivalence relation. So think that these points are irrational. Rational, T1, T2, T3, and if we want to extend the rational lamination to a closed equivalence relation in R mod C, the only way to do it, component of the complement, like going to have that T1 is going to have to be equivalent to T2 is going to be equivalent to T3. So essentially there exists a unique equivalence relation such that extends the rational lamination is closed. So we're using the fact that the limit and is unlinked. And this is this, when represented in the unit disk, that unique extension is effectively a closed set. Okay? And from this follows that, in other words, we recovered the model for the Julia set in the very best and ideal case at the beginning of the talk. Beginning of the talk, I said if it's locally connected, one automatically has this lamination which gives us a model for the Julia set. And in this case, this means that that from the rational lamination one can read this unique model. So the model for the Julia set says that that if one takes the complex plane and mods out by this now, and here pushes down the dynamic of C to the D, and here one has the dynamic of F, then this map is a conjugacy, is a semi-conjugacy. And it's a monotone map which has a lot of good properties, as giving at least a rough model for the dynamics in the Julia set. So for an a priori non-locally connected Julia set, one at least has this.
The Riemann map extends if and only if the Julia set is locally connected, right? I mean, it's just only, that's the capitation thing. How does this connect to the extension?
Oh, and again, if J of F is locally connected, then H is homeo. It's a conjugacy, actually. Okay?
But you don't connect this to the actual Riemann map. You're not extending the map from basic to infinity.
It is.
This is the way.
The problem is the following. Let me draw something. So here's the Riemann map. C minus the bar and the boundary of this. This goes like that. The Riemann map goes there. Okay? If it extends. So, and the extension is, what I'm saying here is just modding out by the identifications of the extension and getting a map which goes to a mod. Okay, so let me talk a bit about so this is sort of some of the things that one gets by analyzing the rational lamination of a polynomial. Given a polynomial, you have the rational lamination. You want to understand its basic properties, and in understanding the basic properties, one starts to learn a bit about the topology of the Julia set. But the of course more exciting direction of that theorem is going back. Is given certain rational lamination with certain properties, given certain equivalence relation which satisfy certain properties, find a polynomial which has that as a rational lamination. And there's an intermediate step here, of course, because this is a pretty abstract description and one would like something more concrete. Something more concrete is given by certain objects called critical portraits, which satisfy certain conditions called a periodic needle. Let me at least tell you a word about that. So what is a critical portrait? Is something was invented by Bielefeld, Fisher, and Howard, or initially by Fisher in his thesis, and then used by Bielefeld, Fisher, and Howard. And I would like to just give a feeling for what it is in the case of cubic polynomials. So in the case of cubic polynomials, it's just either a triple of points in the circle or a pair of pairs, which, so the triple has the property that there's one element, then there's one t plus 1/3 and t plus 2/3. So when one multiplies by 3, all these three elements map to the same element, to 3t. And here, the same story, but with two pairs. What this reflects is that a cubic polynomial can have either one critical point, if it's of the form CQ plus C, and if there are external rays landing at it, automatically there are three external rays landing at it which map to the same external ray. And in the other case is that a cubic polynomial can have two critical points, simple critical points with multiplicity only one, and if there's one external ray landing at that critical point, then there's automatically two which map at the same. So this abstractly sort of tries to capture the location of the critical points through angles in the circle. And the way one can at least associate to a polynomial a critical portrait, so say that you have a polynomial f and you want to associate to that a critical portrait. You a priori don't know that there are external rays landing at the critical points of the polynomial. So what you do is you say theta is compatible with f. If the rays that participate of theta virtually land at the critical points. If is contained where this relation is the unique extension of the rational lamination. So in this sort of way to go to prove realization, one essentially, what one does is, what I'm describing here is how to associate to a polynomial a critical portrait, but actually one can do the same. One then works a little bit harder and looks that one can associate a critical portrait in a similar way when one has just equivalence relation which satisfies that condition, which is maximal. And so to finish, there is a way to then recover this the rational lamination of the polynomial as the critical portrait. So there's an abstract way to reconstruct the rational lamination of this polynomial. And again, one can do the same if one has a maximal equivalence relation portrait, and that critical portrait generates certain equivalence relation in Q mod C, which is equal to lambda Q. So the way that one goes, that is very roughly the way that one moves from here to here and from here to here. I'm not describing this construction in the middle. So, but the main point here is to, once that one has certain a critical portrait, is to try to construct a polynomial which is compatible with that critical portrait. And to do that, one can argue in several ways. Sort of the easier way to argue is that there is sort of a dense road here constructed by Bielefeld, Fisher, and Hubbard, and one can sort of try to extend that dense road by continuity, or one can look in parameter space and try to find a road from a given critical portrait to find a polynomial. That's it, I guess.
Non non-locally connected K. The statement is that you can, if all cycles are repelling, that you can collapse the Julia set down into something which is locally connected.
Yeah.
And if you have any external rays of the Julia set, it will, under the image, it will go to a random converted.
Yeah.
Every limit point is the equivalent of class.
Yeah. And it's nice in the subset of periodic points. I mean, the model and the Julia's the periodic. The pre-image of periodic points are periodic points, the image of periodic points are periodic points.
And is this image on the left, is it a topological manifold or a Riemann surface?
Well, it is a topological manifold, of course. It is hard to, I mean, from the point of view of having this as a conformal map, I guess. That is the question.
So after you've made this collapsing, it's obvious that it's still a manifold?
Well, you use, there's some topological result there from Moore or whatever that you use. Yeah. Huh? But it's
The left piece is still C, is that right? The issue is
no, the issue here is that the left piece is still C, and then there one has to use some theorem to show that it's still C. But obviously, I mean, there are known examples where one can collapse this, and there's no way to put a conformal structure here to make this map the induced map holomorphic.
So how do you relate this space with prime lines of Julia set?
Sorry, with prime ends. So, what is the relation? The preimage of a class of, I'm going to put here a class of T is equal to the union of all S in the class of T of the impression of S. That is the relation.
So there's an intrinsic topological description just on the Julia set in terms of prime ends. You talk about collapsing certain prime ends.
Yeah, but the point is which prime ends you collapse, you have that it comes with information of the rational.